So now let's kind of forget this, but not really. What would happen if we change this claim slightly to for all n and x and z, x equal to 0, h of n is less than 3 to the n? Well, the first thing we have to change is that it's no longer true for 0, right? H of 0 is 1, and 1 is not less than 1, which equals 3 to the 0. It doesn't equal to it, but it's not just straight up less than it. So that means that this, I was going to cross that on red, but I can do that. That means that this inductive, or this base case has to go away. So our claim is really only true for all n bigger than or equal to 1. But wait, how does that affect things? So down here, we kind of want to do the same proof, right? We eventually, so we want to do the same proof kind of down here, except we want to change all these to less than signs rather than less than or equal to signs. I'll highlight that in green. You can't see what I'm working on. Sorry about that. So we'll change all these to less than signs. But the idea is the same idea, right? If you can show that the 3 previous cases are less than 3 to the n, well then hn plus 1 will be less than 3 to the n plus 1. But we're gonna run into a little bit of a snag. And what is that snag? Well, that snag is, let's see here. Well, first of all, right, since we no longer include 0, we want that to go away. Now we're just going from 1 to n because the claim starts to being true at 1. Let's see. So now this, our range where we're assuming our claim is true in our inductive assumptions, like saying I hold up to n, starts at 1. What's the problem with it starting at 1? The problem with starting at 1 is that we wanted to use the fact, right, that the 3 previous cases are always going to follow the claim, right? In order to use the fact that 3 previous cases are going to follow the claim, we need to prove that 3 previous cases are fall between 1 and n. And so let's see, n's greater than or equal to 2, so n's greater than or equal to 1. N's greater, so yeah, so n's greater than or equal to 1, yeah. N's greater than 2, n minus 1's greater than or equal to 1. That's fine, but look at this. If n's greater than or equal to 2, n minus 2 is bigger than or equal to 0. But it's not guaranteed to be bigger than or equal to 1. So if n is bigger than or equal to 2, we could have that n minus 2 is 0. And if it's 0, aka outside of this range, well, we know that h of 0 does not follow the claim. And so that's going to mess up the whole proof down here because we're no longer going to get that things are less than like we want it to be. Because what we want is we want hn here to be less than 3 to the n, hn minus 1 to be less than 3 to the n, hn minus 2 to be less than 3 to the n. But this will fail. We won't necessarily get hn minus 2 to be less than 3 to the n minus 2 because if n is just bigger than or equal to 2, n minus 2 could be 0 and it doesn't work for 0. So we need to avoid that case. We need to avoid the 0 case entirely because it might not work. Or it's not going to work. So what's the easy solution? Let's just start looking at n greater than or equal to 3. Right? Let's change this to n bigger than or equal to 3. This is n bigger than or equal to 3. This is for all for all n bigger than or equal to 3. So now in our proof, let's go ahead and let n bigger than or equal to 3. And then we're still assuming that for everything from 1 to n, we have the claim holds. We want to show that for hn plus 1, the claim holds too. We want to show that this will imply the claim holds. So note, since n is greater than or equal to 3 now, n plus 1 is greater than or equal to 4. But that's fine because 4 is bigger than or equal to 3. And so we can still, that still means we can use the recursive formula. So this by definition of sequence, we can still use the recursive formula. But now note n is bigger than or equal to 3, which is bigger than 1. And n is bigger than 3, so n minus 1 is bigger than 2, which is bigger than 1. And then n is bigger than 3, n minus 2 is bigger than 1, just like we wanted. Thus, n is bigger than 1, n minus 2 is bigger than 1, or n minus 1 is bigger than 1, and n minus 2 is bigger than 1. And everything else is the same. Right after that, we shall further note that n is equal to n, n minus 1 is equal to n. That's still true. And so we can note that all of our n and our n minus 1 and our n minus 2 were all between 1 and n. Thus, by our inductive assumption, hn is less than 3 in the n, hn minus 1 less than 3 minus 1, hn minus 2 less than 3 minus 2. And then we can change all those to less than signs and everything works out. So you can think about that. I'm not going to go too deep into that anymore, but the point is just be careful. You have to make your n big enough for everything to work out. Although actually here, notice now that we have n bigger than 3, we need one more base case. And our base case has to overlap with our first inductive step. So we have let n equal 3. Note h of 3, as we showed above, equals 6. Further, 3 to the 3 equals 27. Since 6 is less than or equal to 27, well, actually I just want less thans here now from doing this proof. Since 2 is less than 3, since 3 is less than 9, since it's less than 27, h of 3 is less than 33. That shores it up. So the point is, the really big point is that in order for our inductive step to work, remember we needed to have the 3 previous cases work. And so that means we were going to need 3 base cases regardless. And so we needed to have these 3 base cases to be true, the 3 previous ones to when it starts working. So just be very careful. Make sure your n is big enough that everything is covered. And if you're ever in doubt, you can always just add more base cases than you need and start this inductive step slightly later than you need. It won't be wrong. It'll be totally safe and that'll be fine. So if you're ever questioning like, oh, should my n be a little bigger? Well, just make it a little bigger and then verify that everything follows what you want to follow, and so you can use everything you can use. Okay, moving on. And we are moving on to a really cool proof. This next one's a lot of fun. All right. Let's go back up here.